Hello, my good friends. My name is Kefsi, and welcome to my online class. Today, our discussion on calculus of several variables will be on Lagrange multipliers. Have you ever thought of how to find the maximum and the minimum of a function depending on two or more variables? Lagrange multiplier is a theorem that helps us to find the maximum and the minimum of a function depending on two or more variables subjected to another function or functions depending on two or more variables. Today, before the video ends, I will take you through what Lagrange multiplier says, how to form an equation from Lagrange multiplier, and how to use it to find the maximum and the minimum value of a function that depends on two or more variables. This will be a very interesting engagement, I promise you, so please come along. So as I said earlier on, Lagrange multipliers is used to find the maximum and the minimum value of a function depending on two or more variables subjected or constrained to another function depending on two or more variables. So we will use it to find the maximum and the minimum value of a function depending on two or more variables subjected or constrained to another function depending on two or more variables. So if we have a function, let's say x, y, and z, and subjected or constrained to another function g depending on x, y, and z, and is equal to k, then we can say the function x, y, and z is called the objective function. The objective function. Then our function g, depending on x, y, and z minus, let's say, k, is our subjective function. So if a problem is given, you are able to locate your objective function and located the subjective function, that's the constraint. Then what did Lagrange multiplier says thereafter? So Lagrange multiplier then says that you find the gradient of this function. That's, remember, the differential operator times the function is the gradient, and it will be equal to lambda times the gradient, the differential operator times the objective function. What happened? So you remember when we are finding the gradient of a function, the differential operator times the function is just a partial differentiation of the function with respect to s plus partial differentiation of the function with respect to y, then partial differentiation of the function with respect to z. The same way applied to this, the partial differentiation of the function with respect to g, the partial differentiation of, plus the partial differentiation of the function with respect to y, then plus the partial differentiation of the function with respect to z, where k is constant. Then in equating like things, remember, please, Lagrange multiplier is saying that this equation is called the optimization equation. So let's take notice of that. Then it simply means that in equating coefficient, you can say the partial differentiation of this function with respect to x will be equal to lambda times the partial differentiation of the function with respect to g with respect to x. Then the partial differentiation of this function with respect to y will be equal to lambda times the partial differentiation of the function with respect to y. Also, the partial differentiation of the function with respect to z will be equal to lambda times the partial differentiation of our subjective function with respect to z. So after we do that, we find the value of x in terms of lambda, the value of y in terms of lambda, and if possible, the value of z in terms of lambda. After that, we substitute it into our subjective function to get their corresponding values of x, y, and if possible, z. Then we'll be able to determine which one is maximum and which one is the minimum. The value of the x, y, and z from our subjective function are known as the extremes. So now we take some sample questions and see how we can find the maximum and the minimum value of a function depending on two or more variables using Lagrange multipliers. So let's look at our first example. They say find the maximum and the minimum value of the function f depending on x and y equal to 5x minus 3y subjected to x squared plus y squared equal to 136. So how do we do that? So we are going to use Lagrange multipliers to find the minimum and the maximum value. Remember our function f is xy, depending on xy, 5x minus 3y. Then our function g of xy will be equal to x squared plus y squared, then minus 136, where 136 is the k constant. So from the optimization equation, we said that the gradient of this function xy will be equal to lambda times the gradient of the subjective function. The gradient of the subjective function g depending on xy. Then equating like terms from the optimization equation, we say that the partial differentiation of this function with respect to x will be equal to lambda times the partial differentiation of the function with respect to the function g with respect to x. Then the partial differentiation of the function f with respect to y will be equal to lambda times the partial differentiation of the function g, that's the subjective, with respect to y. Then, since we don't have z, we don't have problem with that one. So, we know that our f of xy is 5x minus 3y. So what is the partial differentiation of this function with respect to x? Remember, when we are doing partial differentiation of a function with respect to x, the y will be kept constant. You can say the partial differentiation of this function with respect to x will be equal to 5. Then the partial differentiation of this function with respect to x will have 2x. Since this is constant, it will be 0. This is constant, it will also be 0. Then, the partial differentiation of the function with respect to y will be equal to negative 3. And the partial differentiation of the function g with respect to y will be equal to, this is constant 0, this will be 2y, then this is constant, it will be 0. So when we substitute that into our equation, this, we will say 5 will be equal to lambda times 2x. You can have 5 is equal to 2 lambda x. I'll make x a subject. X will be equal to 5 over 2 lambda. That's dividing both sides by 2 lambda. Also, negative 3 will be equal to lambda times 2y. Negative 3 will be equal to 2 lambda y. And our y will be equal to negative 3 over 2 lambda. So now, since we know our x and y, we substitute it into our the subjected function. That's x squared plus y squared equal to 136. So in place of x, we have 5 over 2 lambda all square plus negative 3 over 2 lambda all square equal to 136. 5 squared 25. 2 lambda square will be 4 lambda square. Negative 3 square is 9, so 9 over 4 lambda square equal to 136. So I'll multiply through by the LCM, which is 4 lambda square. We have 25 plus 9 equal to 4 lambda square times 136. 25 plus 9, that will be 34. And 4 times 136 will be 544 lambda square. We divide both sides by 544. We have lambda square is equal to 34 over 544. 34 divided by 544 will be 1 over 16. Then we'll find the square root of 1 over 16. Remember, the square root of every number is plus or minus. Then we can say our lambda is plus or minus 1 over 4. Now, since we know the values of lambda, we substitute it into these two equations to get the values of x and y. After we get the value of x and y, then we can substitute those values into our function. Then we can find the maximum and the minimum. So now we substitute lambda into this equation to get our x and y. So our x will be 5 over 2 bracket. Lambda is plus or minus 1 over 4. We have plus or minus 1 over 4. This will be 5 bracket. 2 will multiply that. We have plus or minus half. 5 divided by half will be plus or minus 10. So the value of s is plus or minus 10. What of the y? Y will be equal to negative 3 bracket 2 times plus or minus 1/4. That's the value of lambda. So we have negative 3 over plus or minus half, and that will give us plus or minus 6. Then we can say our extremes are when s is 10 and when y is 6, and when s is negative 10 and when y is negative 6. That's from these values. So now, since we know the extremes, we substitute it into our function to find its maximum and minimum. So in substituting, we can get one as 5 into bracket 10 minus 3 times 6, 5 times 10, 50, 3 times 6, 80. 50 minus 18, that will be 32. Then also when we substitute the negatives, we have 5 times negative 10 minus 3 times negative 6. 5 times negative 10 will be negative 50. Negative 3 times negative 6, that will be plus 18. This will give us negative 32. So we can say this is the maximum value and this is the minimum value. And the maximum value occurs when s is 10 and y is 6. And the minimum value occurs when s is negative 10 and y is negative 6. So we say maximum value. The maximum value is 32, and it occurs at 10, 6. And the minimum is negative 32 and occurs at negative 10, negative 6. I hope you get this. We'll solve one more example on it so that you'll be abreast with it. So please, let's solve the second example. You can pause the video and try solve it. After that, you compare our answers with mine. They say use Lagrange multipliers to find the maximum and the minimum value of the function f depending on x and y equal to 3x plus 4y constrained at x squared plus y squared. So what do we need? We need our objective function, which is equal to 3x plus 4y, and our subjective function, or the constraint function depending on x and y, which will be equal to x squared plus y squared minus 100. So what do we have? Remember, from the optimization equation, the gradient of the function x, y will be equal to delta times the gradient of the function gy. So in equating like this, remember this is just partial differentiation of this function with respect to x and y. So in equating common coefficients, we can say that the partial differentiation of this function with respect to s will be equal to lambda times the partial differentiation of the function with respect to g with respect to x. Also, the partial differentiation of the function y, the function f with respect to y will be equal to lambda times the partial differentiation of the function g with respect to y. So, our function f, the partial differentiation of that function with respect to s, remember the y will be kept constant, will be 3. And the partial differentiation of this function with respect to y will be equal to 4. And the partial differentiation of this function with respect to x will be equal to 2x. Remember, this is constant, so 0. This is constant, 0. And the partial differentiation of the function g with respect to y will be equal to, this will be 0, then we have 2y. Since this is constant, it's also 0. Now we substitute these values into this to find x in terms of lambda and find y in terms of lambda. So in substituting, you can say 3 will be equal to this times 2x. So our 3 will be equal to 2 lambda x. X in terms of lambda will be 3 over 2 lambda. Also, 4 will be equal to lambda 2y. So 4 will be equal to 2 lambda y. And our y will be equal to 4 over 2 lambda. In substituting this into our constraint, which is x squared plus y squared equal to 100, we'll have 3 over 2 lambda all squared, that's the value of x, then plus the value of y, which is 4 over 2 lambda all squared equal to 100. When we solve this further, we'll get 3 squared 9 over 4 lambda squared plus 4 squared 16 over 4 lambda squared equal to 100. We multiply through by the LCM. We'll get 9 plus 16 equal to 4 lambda squared times 100. 9 plus 16, 25, will be equal to 400 lambda squared. Now our lambda squared will be equal to 25 over 400. And 25 over 400 will be equal to 25 over 400. 25 over 400 will be 1 out of 16. So lambda squared is equal to 1 out of 16. Our lambda will be equal to plus or minus the square root of 1 over 16. Lambda will be equal to plus or minus 1/4. So, since we know the value of lambda, we substitute it into these two equations to get a value of x and y. So on substitute, our x will be equal to 3 bracket 2 times plus or minus 1 over 4, which will be 3 over plus or minus half, and this will be plus or minus 6. Then our y will be equal to 4 over 2 plus or minus 1 over 4, which will be 4 over plus or minus half, which will be plus or minus 8. So we can say our extremes are 6 and 8, then and negative 6, negative 8. So now, since we know our extreme, we substitute into the objective function or the function under discussion to find the maximum and the minimum values. So when we substitute the 6, 8, we'll get 3 bracket 6 plus 4 bracket 8. 3 times 6 is 18 plus 4 times 8 is 32. 18 plus 32, that will be 50. And when we substitute this, we'll get 3 times negative 6 plus 4 times negative 8. 3 times negative 6, negative 18. 4 times negative 8 will be minus 32. Negative 18 minus 32 will be negative 50. Then this is our maximum value and this is the minimum value. So we can conclude that our maximum value is 50 and occurs at 6, 8, and the minimum value is negative 50 and occurs at negative 6, negative 8. I hope you get that. We'll solve one more example on a function that depends on 3 variables so that you have a full arm. So we'll solve our last example on this, but before we do that, please remember to subscribe to my YouTube channel if you are here too. like and comment. Your comment keep me going. So the third question says use Lagrange multipliers to find the maximum and the minimum value of the function f depending on x, y, and z equal to x plus y plus 2z. Constraint at x squared plus y squared plus z squared equal to 3. So how do we do that? Remember our objective function, which is dependent on x, y, and z, is equal to x plus y plus 2z. And our subjective function, g, which is dependent on x, y, and z, will be equal to x squared plus y squared plus z squared, then minus the constant 3. So from the optimization equation, we know that the gradient of this function, x, y, and z, will be equal to lambda times the gradient of this function, g, depending on x, y, and z. So we can deduce that the partial differentiation of this function with respect to x will just be lambda times the partial differentiation of the function g with respect to x. Also, the partial differentiation of this function with respect to y will be equal to lambda times the partial differentiation of the function g with respect to y. Then, the partial differentiation of the function f with respect to z will be equal to lambda times the partial differentiation of the function g with respect to z. What's the partial differentiation of this function with respect to x? The partial differentiation of this function with respect to x. Remember, the y and the z will be kept constant, so this will just be 1. And the partial differentiation of this function with respect to y, the x and the z will be kept constant, so this is 0, then this will be 1, this is 0. And the partial differentiation of the function with respect to z, x and y will be kept constant. This will be 0, this will be 0, this will be 2. Then we find the partial differentiation of this function with respect to x, y, and z. You can say the partial differentiation of the function g with respect to x will be 2x. This will be 0, this is 0, that will be 0. And the partial differentiation of the function with respect to y. This is 0, this will be 2y. This is 0, that is 0. And the partial differentiation of the function with respect to z will be, this is 0, this is 0, this is 2z. Then the constant is also 0. Now, since we know that, we just substitute into this equation to find x in terms of lambda. So in substitute, we can say 1 is equal to 2. So 1 is equal to lambda times 2x. 1 will be equal to 2 lambda x, or x will be equal to 1 over 2 lambda. When we substitute the y2, we have 1 is equal to lambda times 2y. 1 will be equal to 2 lambda y, and our y will equal to 1 over 2 lambda. Then when we substitute the z2, we have 2 will be equal to lambda times 2z. So 2 will be equal to 2 lambda z, and our z will be equal to 2 over 2 lambda. Now, since we know that x, y, and z, we'll substitute into this equation, x squared plus y squared plus z squared equal to 3, to get a value of lambda. So we can say 1 over 2 lambda all squared, which is the value of x, plus 1 over 2 lambda all squared, the value of y, plus 2 over 2 lambda all squared, the value of z, will be equal to 3. When we square that, we get 1 over 4 lambda squared plus 1 over 4 lambda squared plus 4 over 4 lambda squared will give us 3. When we multiply through by 4 lambda squared, we get 1 plus 1 plus 4 will be equal to 3 times 4 lambda squared. 1 plus 1 is 2 plus 4 will be 6. 3 times 4 will be 12, so 12 lambda squared. When we divide both sides by 12, our lambda squared will be equal to 6 over 12. Lambda squared will be equal to half, and lambda will be equal to plus or minus the square root of half. So our lambda will be equal to plus or minus 1 over the square root of 2. So since we know the values of lambda, we substitute back into x y, and z to get their values. So when we substitute, we get a value of x to be equal to 1 over 2. Remember, lambda is plus or minus 1 over the square root of 2, so plus or minus 1 over the square root of 2. This will be equal to 1 over plus or minus 2 over root 2. Then I want to solve this further. That's we reciprocate. We get plus or minus root 2 over 2. The same way, the y will be equal to 1 over 2. Remember, y is 1 over 2 lambda. So 1 over 2 plus or minus. Lambda is 1 over the square root of 2, which will be equal to 1 all over plus or minus 2 over root 2. And this will be equal to plus or minus root 2 over 2 as well. Then the z, remember, is 2 over 2 lambda. So when we substitute, we get 2 over 2 times plus or minus 1 over root 2, which will be equal to 2 over plus or minus root 2 over 2. Remember, if we have 2 divided by root 2 over 2, we get 2 times 2 over. So we reciprocate this. So we get 2 times. So this is, this will be 2 over root 2, So when we reciprocate, we get 2 times root 2 over 2. And this will divide this, we'll get root 2. So we'll get plus or minus root 2. So now we substitute the value of x, y, and z into our function to get a maximum and a minimum. Remember, the extremes will be root 2 over 2 for the x, root 2 over 2 for the y, and root 2 for the z. And negative root 2 over 2 for the x, negative root 2 over 2 for the y, and negative root 2 for the z. So now we substitute into this function. So we get root 2 over 2 plus root 2 over 2 plus 2 times root 2. The LCM is 2, so we have 2. 2 goes here 1, so we have root 2 plus root 2. Then plus, this goes here 2 times, this will be 4 root 2. When we simplify, 1 plus 1 is 2 plus 4, that will be 6 root 2 over 2. 6 root 2 over 2 will be 3 root 2. Then the negative. You have negative root 2 over 2 plus negative root 2 over 2 plus negative root 2. That's negative 2 times root 2. Remember the LCM again is 2. So we have 2. 2 goes here 1. We have negative root 2. 2 goes here 1 minus root 2. Then 1 goes here 2 times, that will be minus 4 root 2. When we simplify, minus, so this is minus 1 minus 1, or minus root 2 minus root 2 will be minus 2 root 2, minus 4 root 2 will be negative 6 root 2 over 2, and that will be negative 3 root 2. So we can say the maximum value is 3 root 2, and the minimum value is negative 3 root 2. The maximum value, remember, it occurs at root 2 over 2, comma root 2 over 2, comma root 2. And the negative value occurs at negative root 2 over 2, comma negative root 2 over 2, comma negative 2. I hope you understand this theorem of Lagrange multipliers. We'll end it here today. Remember to subscribe to my YouTube channel. Like, comment. Please, your comment keep me going. Until we meet again. My name is Kepsi.